Chemistry, we're moving on to Unit 7 now. This deals with something we learned about in their basic forms, which is ionic and covalent bonds. Now we're going to take a little bit of a deeper dive into these topics. Okay, first we're going to deal with the concept of solubility rules. So when an ionic compound dissolves in water, it is referred to as soluble. When an ionic compound only slightly dissolves in water, and that means very, very slightly, it is referred to as insoluble, that it does not dissolve in water. Solubility rules allow us to determine which ions in an ionic bond will dissolve in water. So examples: table salt dissolves in water. NaCl produces sodium ions and chloride ions. Now, this is where it's really important to include the states of matter after the compound or after the ions or the elements. So AQ is aqueous, meaning specifically that it's in water. Silver chloride, AgCl, does not dissolve in water. So only in very minute amounts will you find silver ions and the chloride ions. So effectively we say it does not dissolve in water. So the table below shows the solubility rules for some common ions, and so I'm going to give you some exercises to become familiar with these. Let's look at what it's saying. Over on the left side, it's saying everything in the soluble column will dissolve with anything. It doesn't matter what it's attached to. So lithium, sodium, potassium, ammonium, nitrate, and acetate dissolve no matter what they're attached to. Down below, you see three elements: chloride, bromide, and iodide. They dissolve with anything they're attached to with three exceptions: silver, mercury, and lead. Below that, you see sulfate. That will dissolve with anything it's attached to except the four that you see in the exceptions: strontium, barium, lead, silver, and calcium. Now go over to the right. These are insoluble with anything that they're with. The exceptions, though, are anything in the top row. So lithium, sodium, potassium, ammonium. So OH, hydroxide, is insoluble. It will not dissolve with anything except the three you see in the except parentheses: calcium, strontium, and barium. Same with sulfide. It will not dissolve with anything except calcium, strontium, and barium. And down on the bottom row, you have carbonate and phosphate. They will not dissolve with anything in water. Okay, so when we dissolved eggshells, calcium carbonate, though eggshells don't dissolve in water, but we were able to dissolve them in vinegar. So let's do some exercises. So look at the sheet, look at the solubility rules sheet in your packet. So take a minute to get that out. So let's look at KCl. So it's got potassium and chloride. Will it dissolve in water? Yes. Potassium K dissolves with anything. What about AgCl? No. Chloride dissolves with anything except three elements, and silver, Ag, is one of those. So no, that will not dissolve in water. What about calcium hydroxide? Yes. Hydroxide will not dissolve with anything except for the three elements that you see on your sheet, and calcium is one of those. How about strontium sulfate? No, that will not dissolve. Sulfate, SO4, will dissolve with anything. It will dissolve with anything except five elements, and strontium is one of those five. So strontium sulfate will not dissolve. Silver nitrate. Yes, it will dissolve. Nitrate dissolves with absolutely everything. That's in the upper left-hand corner of the table. How about calcium sulfate? Yes. It should be sulfide, actually. Sulfide does not dissolve with anything except hydroxide, calcium, and one other, and so it will dissolve. How about magnesium sulfide? No, sulfide will not dissolve with anything except a few elements, and magnesium is not one of those. How about lead chloride? No, chloride dissolves with anything except three elements, and one of those is lead. How about potassium iodide? Yes, potassium K dissolves with anything. No exceptions. And finally, how about barium sulfate? No, sulfate SO4 will dissolve with anything except 5 elements listed on your table, and barium is one of those that it will not dissolve with, so no, that will not dissolve. So I'm going to ask you to do the last 5 on your own. Okay, now we're going to go through an exercise which I really like because it allows you to review everything, or not everything, but a lot of things that we've done in this course. Some of them you may have forgotten, but this is a chance to remember them again and relearn them. And what we're going to do is create a net ionic equation. And what a net ionic equation is it's a chemical equation. We're going to start with a double replacement reaction with ionically bonded compounds, and we're going to end up with the equation that shows only those elements or compounds that actually take place in the reaction. And it's going to eliminate any that don't actually take place in the reaction. So that sentence may not make any sense to you at this point, so you'll see what it means as we get to the end of this problem. Okay, because there's going to be 9 steps, and I lay them out on your sheet step by step. Okay, this is a good review of many of the concepts we've done before, so let's get started. So a net ionic equation displays the reactants and products of a reaction that take part in the reaction. Net ionic equations are usually carried out by double replacement reactions. The elements or compounds that do not take part in the reaction are called spectator ions, because they're like spectators at a football game. They just sit off to the side and watch the reaction take place, so they're spectators. In the next 2 examples, you will, I believe there's just one example actually now, you will determine the net ionic equation for the reaction. So you need the following reference sheets: the 60 common ions, the solubility rules, and the charge numbers by ions. So, example, write a net ionic equation for the reaction between potassium sulfate and calcium iodide. So right off the bat, you're being tested on something. Do you remember your chemical names and how to convert those into formulas? So let's go ahead and do that. You should have your 60 common ions and your charge number by ion sheet. So write the chemical formula for the 2 compounds. So using the periodic table and the 60 common ions sheet, identify the symbolic names for these reactants. You are familiar with potassium, calcium, and iodide. Sulfate is a covalently bonded ion SO4. So potassium sulfate is going to be KSO4. You put it together with the SO4. Again, that comes off the 3rd section on your 60 common ion sheet. Calcium iodide is CaI. So there you see a portion of your 60 common ions, and you see sulfate down there in the lower right, SO4 2-. So sulfate has a 2- charge. Step 2 of 9 steps. Create a double replacement reaction by switching the cations and the anions. So there you see what we did. We took the K and the Ca, those are both the cations, those are the metals, and we swapped places. So that the Ca is with, after the reaction, is with the SO4, and the potassium, the K, is with the iodine. So you just switch dance partners here. You see how that works? Okay, and there's the charge number by ion sheet. So step 3, determine the charge number of each element or compound. Use the 60 common ions that you were just shown and the charge number by ion sheet that you were just shown there. So you have those in your packet. So there's the formula. So we're going to go ahead and place the charge number based on those 2 sheets. Potassium has a 1+ charge. You should be able to locate that right now on your charge number by ion sheet or your 60 common ions. It has a 1+ charge because it likes to give up an electron to be like the nearest noble gas, and so that gives it a 1+ charge. SO4 has a 2- charge. That you can only find on your 60 common ion sheet, and that's in the third section that was shown on the previous slide. Calcium has a 2+ charge, no other possible charge, and iodine has a 1- charge. Now we go over here, calcium is still 2+, sulfate is still 2-, potassium still 1+, and iodine is still 1-. So you can see that the KSO4, the CAI, are not balanced. They're not charge balanced. Whereas on the product side, calcium sulfate, CaSO4, and potassium iodide, Ki, are charged balanced. They have the same number of positives as negative. So what we need to do is use the crossing arrows method to put subscripts on the KSO4 and the CAI. So this is something that we did some time ago. So step 4, adjust the subscripts to balance the charges in each compound. So we need 2 potassiums, 2 Ks for every 1 SO4. Since K is only a +1 and SO4 is a 2-, we need 2 of the +1s, 2 times 1 is +2, to balance out the 2-. Similarly with the calcium iodide, calcium is a 2+, iodide is a 1-, so we're going to need 2 of the iodides. 2 times 1- gives you 2- to balance out the 2+. And as we said, everything on the product side is already in balance. So these are the proper subscripts, so now everything is charge balanced. So 2 potassium and 2 iodide were required to charge balance the reactant side. Solubility rules describe which ions will dissociate, dissolve in water. All of the ions in the left column will dissolve with any ion except for those shown as exceptions. All of the ions in the right column will not dissolve with any ions except for those shown as exceptions. So step 5, use the solubility rule sheet to determine if the compounds will form a solid. So take a look at these. So if we look at the first compound there, K2SO4, potassium dissolves with anything, no matter what. So that will be aqueous. Aqueous means it's going to be dissolved in water. It's not going to come together as a solid. Calcium iodide. Iodine dissolves with anything except 3 elements, but calcium is not one of those 3, so calcium iodide will dissolve. So it becomes aqueous. Now we go over to the right and we have calcium sulfate. Okay, so let's go back and look. So we see down in the bottom left corner that sulfate dissolves with anything except 5 elements. And calcium is one of those 5 exceptions. That means calcium sulfate will not dissolve. They will stay together in water. So that is going to be a solid. And finally, potassium iodide over on the far right, potassium dissolves with anything. So those two are not going to come together. Even though they're written in the formula as though they're a compound, they are not. They will stay dissolved as potassium ions and iodide ions. So the only solid we're going to have here, and there's no guarantee you're going to end up with a solid when you do one of these reactions, but we do here. The only solid is the calcium sulfate. So K is soluble with anything. Iodine is soluble with calcium. SO4 is not soluble with calcium, so therefore it's solid. And potassium, again, is soluble with everything. So K2SO4, CAI, and Ki dissolve in water and remain dissolved, and they are in aqueous solution. This means that they are not compounds when they're in water. When they're on dry land, when they're not wet, they will stay together as an ionic compound. But the moment you put them in water, the water molecules are going to pull them apart, those 3 compounds. CaSO4 does not dissolve in water. This means that it will form a solid called a precipitate. Precipitate is simply a solid that will, generally speaking, sink to the bottom of the vessel, the container. Okay, so now we're on step 6. We've got to balance the equation just like we've done before. You can use the box method if you want. Here we'll just count atoms. So on the left we have 2 potassiums. On the right we have 1. On the left we have 1 calcium. On the right we have 1. On the left we have 2 iodines. On the right we have 1. and on the left we have 2 sulfates. On the right we have, one sulfate. On the left we have 1 sulfate, on the right we have 1 sulfate. And remember that SO4, being a molecular ion, is not going to dissolve in water. In other words, the sulfur and the oxygen are not going to break apart. So you can treat those like an element. They're going to stay intact on both sides of the equation. Okay, so what do we need to balance? Well, we need to put a 2 in front of the Ki. When we do that, the K becomes a 2 on the right side, and the I also becomes a 2 on the right side. And now you see everything is in balance. You have everything matches up right side, left side. So therefore, that's a balanced equation. Step 7. Separate all ions. This is called the complete ionic equation. When you do this, start way over on the left side of your paper. I mean all the way to the edge, because this equation, and don't write too big, because this equation could stretch all the way to the right side of the paper. It's very long. So let's take a look at this. This is going to seem like the most complicated part. It's not. So the potassium sulfate, that breaks into 2 potassium ions. It's not a K2 molecule. There's no such thing. It's 2 separate K ions that are in 2 different locations, plus a sulfate. So those are both aqueous, and we see that the charges, the potassium has a 1+ charge, but you have 2 of them, so you have 2 1+ charges. Now we go to the calcium iodide, and the calcium has a 2+. The iodides have a 1-, but you have 2 of those to balance that out. Now you go over to the right side, and the CaSO4 we said did not dissolve in water. It remains as a solid, so you do not break that up into ions, nor do you show the charge numbers above it. It's just simply a solid. It's an ionically bonded compound that will stay together in water. And finally, over on the right, we have the potassium iodide. That's a 1+ charge, 1- charge, and you have 2 of those from your balanced equation. You have 2 of those. Okay, so this is called the complete ionic equation. Now we go on to step 8. So all ions listed as AQ are separated. CaSO4 is not soluble in water, so it forms a solid compound. Since this compound frequently sinks to the bottom of the vessel, it is called a precipitate. Step 8. Eliminate all ions that appear on both sides of the equation. So there's the equation, and we see, first of all, that the K's, 2K 1+ appears on the left and 2K 1+ appears on the right side of the equation. So what that means is that the potassium does not participate in the reaction. It starts off as 2 potassium ions. It ends up as 2 potassium ions. So that's what we mean when we say it doesn't participate in the reaction. You know, your first instinct is to say, well, sure, it participates. It's part of the compounds that we're using. But it doesn't join with anything else, and therefore we say it does not participate in the reaction. So that those 2 get scratched. Next, we have the 2I1- on the left and the 2I1- on the right. It has to be exactly the same. 2I1-, 2I1-. And since it starts off as 2 iodide ions and it ends up as 2 iodide ions, it doesn't participate in the reaction. Now, what did not get canceled out? Well, the sulfate there on the left did not cancel out with anything on the right. The calcium on the left did not cancel out with anything on the right. And the CaSO4, which is our solid, did not cancel out with anything on the left. So those are the only compounds or elements that appear in our net ionic equation. We got rid of all the things that aren't participants. They're called spectators. 2K1+, 2I1- are called spectator ions because they just sit off to the side and watch the reaction take place. So the eliminated ions are not part of the final net ionic equation. And so here's our final step. Step 9, write the final net ionic equation. So it's just that last equation without the crossed out elements. So that's SO4 2- plus Ca2+ gives you CaSO4, and that is called a net ionic equation. And there it is. And that takes care of this lesson on net ionic equations. It's a little bit long. I really like to teach this because it does get you to review some of the older concepts that you haven't reviewed in quite a while. Okay, so we'll see you on the next lesson.